Okay, this week in the tutorial questions, you have a question that's quite closely linked to the one that you have in your assignment. There's an example of the question here. I'll try and focus up. You can download it, I'll put a link in the video description. But essentially you're looking at a ray of light that's incident on a plane surface like this, bounces back off, and what we know is that the law of reflection states that the angle of incidence, this angle here, should equal the angle of reflection, this angle here. So this should be a nice symmetric diagram. It's not, because they are asking you to prove that this is the case. So we're going to start off by doing this, and eventually we'll come out with the law of reflection. So start off with, as we do with every physics assignment, we are going to draw every physics problem rather, we're going to draw a diagram. And I'll draw the diagram a little bit bigger than what we've got on there, and it will look something like this. We'll draw it off scale just to keep things simple. Like this. It's A, this is C, O, B, cobbed. They call this distance here x. And we'll come back to why that is and why that's useful, and that's pretty much it. So a light ray is coming down there and coming out here. So Fermat's principle, what this actually states is that the light, the reason it has all these weird properties is actually because it takes the path which requires it to have the least time. Right? So what we're going to end up proving is that the reason that the angle of incidence equals the angle of reflection is that this is actually the minimum amount of time it would take for light to traverse this distance here. This to go from A to bounce off the surface and go back to B. Right? Which is actually quite an interesting point. But onto the assignment question. What we need to do is we need to figure out a way of calculating the total amount of time it takes light to get down this path. And that's actually really simple. If it was a person walking down here, all we do is we would look at their velocity and use their velocity and the distance that they travel to figure out the time using this formula. Velocity equals distance over time. Alright, so all we really need to do to figure out time is figure out how far the distance is. So we could write an expression for the total distance of the trip, which is a naught plus distance is a naught, this here, plus OB. Great, fantastic. But we don't actually want distance, what we want is time. And you can see using this formula here, if we rearrange it, that time is just our distance divided by our velocity. So if we want to turn this into time, we just need to go a naught divided by v, which is the velocity of our light, which of course is going to be c, but I'll call it v to keep it general here, because the speed of light isn't always c, as you'll see in your assignment questions, and ob divided by v, like that. The problem with this is that what we want to do is we essentially want to differentiate this expression. And what that will allow us to do is we're going to differentiate it and set it equal to 0. And hopefully you should know from your calculus that that will give us the stationary points of this function. So that'll either give us the maximum amount of time or the minimum amount of time. The problem is that we don't really know what to differentiate this with respect to. That's why they've given us this x up here. We want to differentiate with respect to x, but unfortunately x is tied up in both of these terms, and it's not clear how. So the next step is going to be reformatting this part of the expression here so that you can see it in terms of x. That means you'll be able to differentiate it. And doing that's actually really simple. So for starters, let's take a look at this triangle here. Ignore this one for the moment. Using Pythagoras, we can write that a naught, so the length of this side here is just the square root of the sum of the squares of the other sides, which is x squared, that side there squared, plus ac squared, like that. And we can do exactly the same for this triangle here. So we can rewrite that OB is the square root of OD, this length here, OD squared, plus BD squared. Great, that's fantastic. Except this has x in it, and this kind of sort of doesn't really. So we want to take another step for this side, and we want to re-express this OD, this length here, in terms of x. Because when you think about it, this distance is going to change when this point changes. If this angle is larger, then it's going to hit down here. If this angle is smaller, then it's going to hit down here, and both our x and this bit are going to change. So to make this a bit easier, I'm going to define a new length. I'm going to call the length between here and here the letter d, for simplicity's sake. And now we can see that this distance here is just d minus c. And there is d minus x, not d minus c. What that means is we can re-express this now in terms of that. So let's do that. It's just going to be OD is now d minus x squared plus bd squared. Okay. Now we've got expressions for A0 and A0 or AO and OB in terms of x. So we can just substitute them in. So this term here is going to become the square root of x squared plus AC squared on V plus this one square root of d minus x squared plus bd squared all over v. Okay. Now, this is the step, this is what we want to get it to. Now all we need to do is differentiate this expression here, set it equal to 0 and solve, and that will tell us at what relative positions of x and d will give the minimum travel time for the light to travel from A off the surface and then back to B. Okay. But we have to do the derivative for that to work. And the derivative of this is actually really simple. Just remember your standard rule for derivatives. If we've got something, say, n to the power of a half, right, if I take the derivative of that, so if this is y, then the derivative y prime is just half n to the power of minus a half. And remember that n to the half is exactly the same as the square root of n. So we're going to use that trick on both of these two. But if the inside of if the inside of this bracket also needs to be differentiated, so we'll have to do that and multiply it through as well. And we'll just show you how to do that by doing the first term here. So this is our derivative. So I'm going to write dt by dx because we're deriving with respect to differentiating, with respect to x. So this first term, what we're going to get is we're going to get a half coming out the front like we did down here. So it's going to be a half. And then we're going to be left with this. So the derivative of that is this, let me write it in terms of this, x squared plus ac squared to the power of minus a half. See, this is exactly the same as that. The only difference is we need to multiply by the derivative of what's inside the brackets as well. AC is a constant, doesn't depend on x at all. X does depend on x, and the derivative of x squared is 2x. So this is going to multiply out by a factor of 2x, and don't forget, we've still got this v from before. And you'll see this term and that are going to cancel out. So we'll end up with x squared times x squared plus ac squared in brackets to the power of minus a half. Now let's do the second term. The second term is pretty much exactly the same format with one little difference. So we're going to get a half out of it again. We're going to get d minus x all squared plus bd squared to the power of minus a half as we did before. And we're also going to have the derivative, so this is going on here, of what is inside the brackets. And if you can imagine expanding this out, you'd have d squared minus 2dx plus x squared. That's what the expansion of that is. And when we take the derivative of that, the d squared term disappears because it's a constant. The minus 2dx term, that becomes minus 2d. minus 2d, and the x squared term becomes plus 2x, all over v. So now we can see that these 2's will cancel, that will disappear, and we are going to be left with, he says, changing to another piece of paper, moving up the page, to write this well explicitly, dt by dx is then x over v times x squared plus ac squared to the power of a half, square root. So that's exactly the same as this. I've just taken it down the bottom because it's a negative power, so it belongs down the bottom, plus this term here. And if I clear it all up, work through the algebra yourself, it's going to become minus d plus x over v times d minus x squared plus bd squared to the power of a half. Okay, now, unfortunately, we're very, very close to a solution, but there's one horrible problem. And the horrible problem is this bit up here. So I could actually rewrite that in the other way around, x minus d. And the problem is that this doesn't match up with this anymore. It's the wrong way around. And what we want to do is keep it the right way around for the reason you'll see in the next step. And to do that, I can just take a minus 1 out of here. So I can reverse that order back to d minus x. If I then take a minus 1 out here and turn all of that into, just a minus like that. What that means now is that this here, the entire term other than the v, is actually just an expression for the relative lengths of two sides of that triangle we started off with. So if I go way back up to the beginning where we started, way back up here, we can actually see that x, this length here, divided by the square root of the hypotenuse, right? That's actually just SOHCAHTOA. So if you remember your sine, if I show it like this, we can also express this triangle here in terms of SOHCAHTOA. So I can write sine alpha equals the opposite, which in this case is x, over the hypotenuse. And the hypotenuse is this bit here. So x squared plus ac squared to the power of a half. So that means this entire term here can be rewritten as sine alpha over v. And you want to guess what the second happens to the second term? Yep, it's exactly the same thing. Sine beta equals d minus x all over bracket d minus x squared plus bd squared to the power of a half. So this becomes that plus sine beta on v. Oh, minus sine beta on v. That minus is really, really important because what we've got now is a simplified expression for dt by dx. The point of this, though, was to solve this expression for alpha and beta, or for x and d, when it's equal to 0, because that will give us the minimum time it takes light to travel from A off the surface and then back to B. So if we set this expression equal to 0, what you can see is that for x to be equal to 0, we have to have sine alpha over v equal to sine beta over v. The v's cancel, we have to have sine alpha equals sine beta. Therefore, alpha equals beta, and the angle of incidence is equal to the angle of reflection, and our proof is done.